All right. The fact that one of your other teachers talks about something similar to this a lot is going to be helpful. A normal distribution. It is continuous. That's one thing you should probably know. It's still a probability distribution, and obviously we still have a random variable. The fact that it's continuous basically tells us that it does pretty much keep going on, kind of like that measured thing. You know, that what was the pounds of sugar we had on the quiz there? You know, that'd be measured, and could that technically go on forever and ever? I think it could. Okay, so there's really no stop to that, which makes this an interesting topic and makes some students struggle a little bit. So if you find yourself struggling a little bit, let me know. Normal curve, you know that as sometimes referred to as something else. Bell-shaped curve at times. What it really is just the graph of the normal distribution. And normally it does look like a bell. And in fact, you've actually seen one of those already when we talked about the empirical rule. 68%, 95%, 99.9%. And you're going to see that again, obviously, in this chapter because it's talking about normal distributions. That's your bell-shaped curve. But you might notice in a true bell-shaped curve, those two endpoints don't get all the way down to the axis. They hover a little bit because there's always that little bit each way that it could keep going. Yeah, sometimes referred to as something not so nice by another teacher, yeah. Because they're beyond 3 standard deviations, and so they're inflection points. Here's where calculus comes in handy. But I'll teach it to you relatively quickly. Points where the graph changes from concave up to concave down, or vice versa. Well, that was pretty good. Well, till the very end there. Then it got a little off. There's your normal curve. Concave down, I kind of call the frown. Concave up is kind of more the smiley face, right? So that's how we look at it in calculus. There's actually 2 points of inflection here. You can kind of see how this is a parabola that kind of opens up over here, right? And so is this over here, right? So those would be considered concave up. Obviously, if the parabola kept going, it would do that. That's not what happens, but you see how it's kind of a smiley face there? And then obviously maybe in a different color, we'll do the frown. You see how basically there, it's a frown, right? So that right there, the place where it switches over from one to the other are your points of inflection. The really neat thing about those points is they happen in a very particular place. It doesn't matter, because you could have a normal distribution that's very flat, as long as it's symmetric, right? And what you need to know about that normal distribution is what goes here. What do you suppose goes there of the data? The mean, very good. And do you agree that that also has points of inflection, that last one I drew, right? And I would say in that last one, they're probably more, well, that's kind of up, that's kind of down, right about in here, right? Give or take, right? It should be symmetric, but I did it by hand, okay? Those will happen 1 standard deviation from the mean. Yeah, how's that happen? It's amazing. All right? And you notice how it goes either way. So your mean is here, and this is 1 standard deviation that way, 1 standard deviation that way. Who remembers the percentage that falls in there? Yeah, one of you did really well with that. Yeah, it's 68, right? And so how much each way? 34. Yep, 34 each way and 68 total. Those are slightly rounded, but close enough. For our purposes, that's way close enough. All right. So those are within 1 standard deviation. That's where those points of inflection happen. Well, here I've given you a distribution A and B. They are both normal because they are symmetric. Now the question is, which normal curve has a greater mean? Now, why A? Because it's taller? Ah, very good. It's not because it's taller. That's what some people say. It's taller, so A has to have bigger, right? But what if A was over here? Does it still have the greater mean? Where do you look for the mean? Middle. There's 15. What's the mean of this one? 12. What's the mean of this one? We'll call this C maybe or whatever. Okay, just because it's taller doesn't mean it has a greater mean, okay? But if you look, basically the mean always falls in the middle. So the mean of A is 15, the mean of B is 12, the mean of this one over here, C, is 6. So which one has the greatest mean? Well, A does. And it's because the middle of it is at 15. But then which one do you believe has the greater standard deviation? So you go and you try and find those points of inflection, right? So you see this one's right about there and there, right? So that standard deviation isn't very far, is it? What is it, maybe 1 or 2 maybe? That way, and 1 or 2 this way maybe, right? But if you look at the other one, maybe we'll color code it here. This one kind of switches over, oh, I don't know, about here maybe? What would you say? And there, do you see how that's, look at that thing. We're going from here all the way over to there and all the way, that's huge. Well, it's not huge, it's only like 4, but, you know, it's much bigger than 1, right? And so that one has a much bigger standard deviation. So you're starting to see finally the payoff is starting to come with this vocabulary. We're starting to get to some more calculations, but you have to know what those words mean. Again, you know, forgive me for the pun. So why don't you go ahead and try and answer the question here. Did everybody see which ones A, B, and C are? I know the copy didn't come off very well there, did it? But I think you can tell which one's A, which one's B, and C. And so which has the greater mean and which has the greater standard deviation? So obviously one of those 3 is going to be left out. But you are told they are normal, and they look symmetric, don't they? They look pretty good. And the mean is going to be in the middle then, and the standard deviation is at those points of inflection. So obviously A has to have the bigger mean, right? It's taller. Oh. Well, which one has the greater mean then? B. Why is that? Because if you look at that, really, what would this be called if we were talking geometry? A dotted line, not quite what I was looking for. Line of symmetry, very good. So the mean there is 60. Hey, what can you tell me about A and C? They have the same mean, don't they? Then how come they don't look the same? Ah, the deviation is different, very good. But if you put that line, look at that, they're both what, 45 for a mean? Where B has 60 for a mean. So yes, B, so greatest mean, the correct answer is B. How about the greatest standard deviation? Why C? Yeah, you can kind of, it's wider, right? I mean, you look at it that way, right? And so basically the difference between A and C is, as we were told, the deviation, because where's the, boy, this thing's really tiny, isn't it? That one's pretty small, but then this one's actually way out here, right? And this one's also pretty small, right? So the biggest is obviously down there for C. Any questions on that so far? Not too bad, right? All right. Well, let's have you actually, can you read those numbers? Oh, 80, 85, 90, 95, 100. I would like you at right now, why don't you actually go and try and estimate the mean and the standard deviation for this one. All right, well, let's see what you came up with here. What do you think the mean is? Yeah, probably pretty close to 90, right? Obviously, we don't know for sure, but we could get a pretty good guess, kind of bring down that line. It's pretty close to 90, right? So we'd say the mean here, and that's mu, remember, is what, 90 feet, right? And this is, yeah, what do you think? So what did you do to figure that out? Yeah, you found the curvy thing. What's that called again? Point of flexion. So this one's kind of concave up, kind of concave down. What would you say about here? Does that look pretty good, you think? How about over here? Well, it's got to be symmetric, right? So it's about the same place. So let's just do this, right? Yeah, and then you work your way down about there, wouldn't you say? Now, standard deviation, you just give it in one direction. And as I said when I wasn't recording here, is why is the standard deviation technically positive and negative? It's technically positive and negative because we take the square root to get it. Right? We weren't told to take the square root, but we just do, and so it is positive and negative. So what do you think that is? It looks about maybe 4 or 5, something like that, right? So we'll say we better go with approximate then, huh? Because it falls a little short of that 85, doesn't it? It falls, because here's 95, right? It falls a little short, I think. Again, if you show me where your points of inflection are and come down, I'll understand. Okay, that's the key to know that it happens at those. And I'd say it's about 4 feet, probably, right? I think the actual answer is about 3.5, but they have inside information. They know the data, so that's a little unfair on their part, right? But I'd say that's about where it switches over. So any questions so far? Not going too bad, right? Number distributions aren't that bad. Basically, the area underneath, there's your empirical rule kind of again. But you notice here they do mu plus 1 standard deviation, mu plus 2 standard deviations, mu plus 3, and then that unnice word that is given to those way out tails out there. The area underneath there, I know that it's weird because these little tails out here actually never really touch. There's always just that little itty bit, okay? And there's always that little itty bit as you go out to the right as well. But the total area is 1. Okay, because this whole probability of something happening is 1. And what we do then is we can find those areas underneath those curves, which again is a calculus technique, technically, if you have to do that. But we have tables and things that'll do that for us. That area underneath that curve, if you add it up, is basically going to tell you the probability of that happening. Okay? And these numbers down here are basically the standard values, and we're going to talk about that in the next section quite a bit. We're going to be using values along there quite a bit. The key to notice is where is 0? It's at the mean. So if I told you that it had a standard deviation of 1.5, you really could go both ways, right? What we're going to start doing is we're going to start talking about what's called a z-score. And the z-score is going to be positive or negative, so it tells you exactly which way to go. So if I told you a z-score of 1.5, do you go both ways? No, you go to where z would be a positive 1.5, and where would that be? In between 1 and 2, correct? If I told you a z-score of negative 1.5, do you go to the same place? No, you go out here, negative 1.5. That's where you would go, okay? But you have to make the connection that they base all those numbers off of 0, which is at the mean, okay, at mu. Okay, if you can do that, positive to the right, negative to the left, you'll be fine. We'll talk a lot more about that when we do those notes. Well, let's actually try one. An adult IQ score, or those scores, they are actually normally distributed fairly well. Okay, mu is 100, and that is actually true. And standard deviation is 15. That's also very accurate. Estimate the probability that a randomly chosen adult has an IQ between 85 and 145. Well, what we're really going to kind of do is we're going to kind of standardize it. Because if we standardize it, we can use that. And so you can just go above and put these values in, right? It's just right above there. So for us, what goes in the place of 0 for us is 100, right? And then what should go over here where they have a positive 1? If my standard deviation is 15, I'm only going 1 standard deviation, right? So what should I put there? 115, right? Well, we have to go, what, 145 and 85, right? And so what should I put at the 2? 130, right? And then out here is your 145, and then beyond that is, again, yes. And then so we have to do the negatives as well, though. So we're subtracting a standard deviation. So over here is 85, and then the next one would be 70, and then yeah, that 15, I tell you, that's a tough one to add and subtract. All right, so we got to find out basically what's the probability. So we have to find basically just those percentages, because you read these percentages could be written as decimals, right? And so what we have to do then basically is just, well, where's 85? 85's right here, right? And go all the way to 145, which is right there. Do you agree? So basically we have to find out do we have the probability of 100%? Do we have them all? No, that's if we had the whole graph. We don't have it all. Do we have just a portion of it? Yeah, our job is to figure out, well, what portion of it do we have? And so you just go ahead and you add up those percentages. Some people just add up the percentages, some look at the decimals. And so, but I want you to see that little area thing, because those of you that have had calculus know that that's integration. So this one right here is included, correct? That little sleeve there, and that's 0.34, at least that's how I look at it, plus that one's included, right? Another 0.34, plus is this one here included? Yep, so 0.135, plus, how about this one? Is this included? How do you do that one, though? Yeah, be careful, 0.0235. How about this one out here? Should I include that one? This one? No. That one? That one? No. I only want those. I only want the ones in between. So you go ahead and you add those up, or you could always do 1 minus the ones you don't want, right? With the complement, it's the same thing. 1 minus these ones I didn't use. And you add those up, and is it a pretty good percentage? What percentage is it? 83.85. Like that, or you could say and so what we'll do a little bit later is I believe anybody with an IQ over 140 gets tagged a genius. Well, 140 doesn't fit here, does it? Well, we'll figure out a z-score for that as this goes on, and we'll figure out how many standard deviations away you have to be. Obviously, it's between what and what? Between how many standard deviations? Between 2 and 3 standard deviations will get you to that tag. Okay. There's also an unfortunate tag for somebody below 70. Okay. There is some kind of, normally if you are that, there is some kind of disability, is what they will put on you there. Okay. If you are below 70. But you got to realize the average changes for your age. I mean, the average stays at 100 for your age, but what you're expected to do does increase. Okay. I do know, but I only got tested once, so it might have been an unfair test. So it's not a good sample, so to speak. Either way. So do you have any questions about this normal distribution deal here? Graphically, it's not that hard, is it?